Look up at the night sky on a clear evening, and one celestial body always stands out: Saturn, the jewel of our solar system. Even through a small telescope, its shimmering rings take your breath away, a cosmic masterpiece suspended in the darkness. But behind that breathtaking beauty lies a world of mysteries so profound they've puzzled scientists for generations. This isn't just a planet, it's a riddle wrapped in bands of ice and gas, whispering secrets we're only beginning to unravel. Think about this: we've sent probes millions of miles through space, captured stunning images of Saturn's swirling storms, and mapped its intricate ring system in astonishing detail. Yet, the more we learn, the more questions emerge. Why does Saturn's North Pole harbor a perfect six-sided storm, a geometric anomaly defying nature's usual chaos? What lurks beneath its dense, golden clouds where pressures could crush a submarine like tin foil? And how do its rings, those dazzling ribbons of ice, continue to behave in ways that stump even the sharpest astrophysicists? The truth is, Saturn doesn't just challenge our understanding, it taunts us, daring humanity to dig deeper. That's exactly what we're about to do. In this journey, we'll uncover 25 of Saturn's most bewildering enigmas, from eerie radio emissions with no clear source to moon-sized objects vanishing without a trace. Some of these mysteries might hint at forces beyond our current science, while others could rewrite what we know about planetary formation. So buckle up, because by the time we're done, you'll never look at that shimmering ringed giant the same way again. The cosmos loves a good puzzle, and Saturn, it might just be the greatest one of all. Of all the strange wonders in our solar system, nothing quite compares to the uncanny sight lurking at Saturn's North Pole, a perfect hexagon stretching wider than Earth itself, etched into the atmosphere like a colossal celestial tattoo. This isn't some trick of the light or camera artifact. For over 40 years, from Voyager's first glimpse to Cassini's breathtaking close-ups, this six-sided storm has stubbornly maintained its shape, defying everything we know about planetary weather. On Earth, hurricanes spiral into familiar curves, governed by fluid dynamics that favor circular motion. But Saturn's hexagon, it's as if nature grabbed a ruler and drew straight lines across the sky. What could possibly create such a geometric marvel in the chaos of a gas giant's atmosphere? One leading theory points to deep-rooted jet streams, layers of wind shearing against each other at different speeds, somehow locking into this angular pattern. Picture water swirling around a drain, only here the drain is a planetary-scale vortex with edges sharper than a crystal. Others suggest standing atmospheric waves, rhythmic oscillations trapped like sound in an organ pipe, carving those flat sides into the clouds. And then there's the wild card: what if something deeper, hidden beneath Saturn's churning hydrogen ocean, is orchestrating this phenomenon? The hexagon's precision is unnerving. Each side spans nearly 9,000 miles, and the entire structure rotates with clockwork regularity, completing one rotation roughly every 10 hours and 39 minutes. Even more bizarre, inside the hexagon, nested storms churn like captive whirlpools, yet the outer walls remain eerily stable. It's a puzzle wrapped in layers of gas and ice, challenging scientists to rethink how energy flows in alien atmospheres. While Earth's weather is messy and unpredictable, Saturn's North Pole feels almost engineered, a cosmic secret waiting to be decoded, perhaps the most humbling part. This hexagon isn't just a scientific curiosity. It's a reminder that the universe still holds phenomena beyond our textbooks, where the rules we take for granted simply don't apply. Every time we point a telescope at Saturn's pole, we're staring at a question mark written in the clouds, daring us to understand the impossible. If Saturn's hexagonal storm feels like a cosmic math problem, then the so-called dragon storm is its full-blown horror show. A monstrous tempest that erupts without warning, unleashing lightning bolts 10,000 times stronger than Earth's, then vanishes like a phantom. Nestled in the planet's mid-latitudes, this beast isn't just another swirling cloud. It's a frenzied maelstrom that doesn't play by the rules, appearing for weeks or months before dissipating into the haze, leaving scientists scrambling to explain its erratic behavior. But the real kicker, when it rages, Saturn's atmosphere literally screams. The Cassini spacecraft first detected these eerie radio emissions in the early 2000s, a crackling, hissing noise so intense that researchers dubbed it the Dragon's Roar. Unlike anything else in our solar system, these signals pulse with a rhythm that mirrors the storm's fury, as if the planet itself is growling, the weirdest part. There's no clear explanation for how the storm generates such powerful bursts of energy. On Earth, thunderstorms feed off warm, moist air rising from the surface. But Saturn has no solid ground, just a bottomless abyss of hydrogen and helium. So where's the fuel coming from? Some researchers speculate that deep within Saturn's atmosphere, layers of exotic compounds like water and ammonia might be clashing, creating pockets of electrical charge that bubble up like geysers. Others suggest the storm taps into energy leaking from the planet's core, a hidden powerhouse we've never directly observed. Then there's the timing. Unlike Jupiter's Great Red Spot, a storm that's raged for centuries, the Dragon Storm flickers on and off like a faulty neon sign, making it impossible to predict when it'll rear its head next. Perhaps the most unsettling detail, when the storm vanishes, its radio screams sometimes linger, haunting the planet's magnetic field like a ghostly echo. It's as if Saturn is teasing us, offering glimpses of a phenomenon we can't quite grasp. Every burst of lightning, every roar from the void, forces us to confront how little we truly understand about the forces shaping these alien skies. The Dragon Storm isn't just a weather event, it's a cosmic wake-up call, proving that even in our own solar system, nature still has tricks up its sleeve. Saturn's rings aren't just static decorations, they're a celestial ballet of ice and dust, constantly shifting in ways that baffle even the most seasoned astronomers. Take the mysterious spokes, those ghostly radial streaks that slice across the rings like bicycle spokes. First spotted by Voyager in the 1980s, these shadowy formations appear and vanish without warning, sometimes stretching tens of thousands of miles in mere hours. What's weirder, they're not just drifting debris, they seem to defy gravity, hovering above the ring plane as if some invisible hand sketched them into existence. The leading suspect, tiny charged particles, lofted by electrostatic forces or maybe even meteoroid impacts, dancing in Saturn's magnetic field like iron filings near a magnet. But here's the twist. These spokes vanish when Saturn's tilt brings its ring's edge onto the Sun, only to reappear years later, as if the planet itself is flipping a cosmic light switch. Then there are the propellers, whimsical gaps in the rings shaped like airborne aircraft propellers. These aren't random scratches, they're the footprints of hidden moonlets, chunks of ice no bigger than a football field, plowing through the ring material like snowplows. Cassini spotted thousands of them, each carving its own miniature wake, revealing a hidden population of tiny moons too small to see directly. But the real shocker. Some of these propellers migrate over time, drifting closer to Saturn or farther away, tugged by forces we don't fully understand. It's as if the rings are alive, rearranging themselves in real time, governed by rules we're only starting to decode. And just when you think it couldn't get stranger, there's the rain, not water, but a steady shower of ice particles tumbling from the rings onto Saturn's upper atmosphere. Cassini's final orbits revealed this unexpected downpour, with the innermost D-ring dumping nearly 10,000 pounds of icy material every second. Imagine standing on Saturn. The sky wouldn't just sparkle with auroras, it would glitter with falling diamonds, vaporizing as they plunge into the hydrogen depths. This ring rain might even explain why Saturn's upper atmosphere is oddly warm, as if the planet is wearing a thermal blanket woven from its own shattered moons. The rings are more than a pretty face, they're a dynamic, evolving system, whispering secrets about gravity, electromagnetism, and cosmic collisions. Every time we look closer, we find another layer of complexity, another question begging for an answer. Are these structures temporary, destined to fade in a cosmic blink, or are they sustained by some hidden equilibrium, a delicate balance we've yet to uncover? One thing's certain, Saturn's rings aren't just orbiting the planet, they're rewriting the textbooks. Among Saturn's many bizarre moons, Iapetus stands out like a cosmic yin-yang, one half gleaming as white as fresh snow, the other darker than freshly poured asphalt. It's a puzzle wrapped in ice, a world so starkly divided that early astronomers struggled to believe their own telescopes. When Giovanni Cassini first spotted it in 1671, he noted something peculiar. The moon seemed to vanish when it orbited to one side of Saturn, only to reappear on the other. We now know why. Iapetus isn't just two-toned, it's a celestial doctor, Jekyll and Mr. Hyde, with one face reflecting sunlight like a mirror and the other swallowing it whole. So what paints half a moon black? One theory points to Iapetus's sluggish rotation. It takes a staggering 79 Earth days to spin just once, allowing dark material to accumulate like dust on a slow-moving car. Some scientists suspect this gunk comes from Phoebe, another of Saturn's moons, which spews dark debris as it orbits. Over eons, Iapetus's leading hemisphere, the side that always faces forward as it moves, collects this cosmic soot while its trailing side stays pristine. But there's a catch. The dark material, possibly rich in carbon compounds, absorbs sunlight and warms up, causing underlying ice to vaporize and refreeze on the brighter, cooler side. This creates a runaway effect, intensifying the contrast until one half looks like a charcoal sketch and the other like a frosted cake. Then there's the ridge. Stretching like a monstrous spine along Iapetus's equator, this wall of ice towers up to 12 miles high and runs nearly the entire circumference of the moon. It's as if someone took a walnut and glued its seam around the middle. How such a precise, gargantuan structure formed remains hotly debated. Some argue it's the remnants of an ancient ring system that collapsed onto the surface, while others propose it's the scar of a long-ago tectonic upheaval where the moon's crust buckled under stress. There's even a wilder idea that Iapetus once spun so fast it bulged at the equator, freezing into this bizarre shape before slowing down, the strangest part. These mysteries might be connected. The ridge's shadow could trap dark material on one side, deepening the color split, while its height might influence how sunlight, or lack thereof, alters the surface chemistry. Iapetus isn't just a moon with unusual markings, it's a laboratory for extremes where every feature seems to defy simple explanations. Whether it's the eerie dichotomy of its faces or the impossible geometry of its ridge, one thing's clear: this moon didn't get the memo on how worlds are supposed to behave. And that's exactly what makes it unforgettable. Beneath the icy crust of Saturn's moon, Enceladus, lies one of the most tantalizing mysteries in our solar system, a hidden ocean erupting into space through colossal geysers, spewing water vapor and organic molecules hundreds of miles above the surface. This isn't just a frozen wasteland, it's a world with a secret, one that might rewrite the rules for where life could exist. Picture this: a moon no wider than Arizona, yet its firing plumes so powerful they've created Saturn's faintest ring, the E-ring, a shimmering halo of ice particles stretching thousands of miles. How does something so small produce such cosmic fireworks? The answer lies in Enceladus's tortured interior. Tugged and squeezed by Saturn's gravity, this moon heats up like a stress ball in a vise, flexing until cracks form in its icy shell. Through these fractures, the subsurface ocean, kept liquid by tidal forces, blasts into the void, carrying not just water but salts, silica, and even methane. When Cassini flew through these plumes in 2008, its instruments detected molecular hydrogen, a potential energy source for microbial life. That's when the shockwaves hit the scientific community. Enceladus wasn't just another icy rock. It had all the ingredients for life: liquid water, chemistry, and heat. The only other place we found this trifecta, Earth's deep-sea hydrothermal vents teeming with organisms that thrive without sunlight. But the real magic is in the details. These geysers don't erupt randomly. They're concentrated near the Moon's south pole, along 4 parallel fissures nicknamed tiger stripes. The hottest spots there reach temperatures around -100 degrees Fahrenheit, balmy by cosmic standards, suggesting active hydrothermal vents might be churning below the ice. Even stranger, the plumes pulse in intensity with Enceladus's orbit, as if the Moon itself is breathing, exhaling more vapor when Saturn's gravity stretches it hardest. And then there's the E-ring. Most planetary rings form from shattered moons or captured debris, but Saturn's E-ring is different. It's alive, constantly replenished by Enceladus's geysers. Every particle is a frozen artifact of the Moon's hidden ocean, a snowflake telling a story we're just beginning to read. Some of this material even rains back onto other moons, painting them with a faint, icy glaze. It's a cosmic water cycle with Enceladus at its heart. What does it all mean? For astrobiologists, this tiny moon is a beacon. If life can thrive in Earth's darkest ocean trenches, why not here, where chemistry and energy mix beneath the ice? For now, Enceladus keeps its secrets, its geysers whispering promises we're not yet advanced enough to decode. But one thing's certain: this isn't just a moon. It's a locked door, and behind it could be the answer to whether we're alone in the universe. If Saturn's other moons play by the rules, Hyperion is the cosmic rebel, a tumbling, misshapen chunk of ice and rock that looks like it's been hit by a celestial shotgun. Imagine a giant sponge left floating in space, its surface pockmarked with deep, shadowy pits, some as wide as football fields. This isn't just any cratered moon. Hyperion's craters are so densely packed, they create a porous, honeycomb texture unlike anything else in our solar system. Even stranger, the bottoms of these pits are coated in a bizarre dark material, reddish-brown and sticky-looking, as if someone smeared cosmic tar across the inside of each cavity. What makes Hyperion truly bizarre isn't just its appearance, it's how it moves. While most moons rotate predictably, Hyperion spins like a drunken top, tumbling erratically with no fixed axis. One day its north pole might face Saturn, the next it's flipped upside down, wobbling under the gravitational pull of its massive neighbor, Titan. This chaotic rotation is a direct result of Hyperion's absurdly low density, about half that of water. If you could drop this moon into an ocean, if it didn't dissolve first, it would bob like a cork. Scientists suspect it's mostly empty space inside, a loose pile of icy rubble barely held together by gravity, which explains why even small impacts can carve out such enormous craters without shattering it entirely. Then there's the mystery of that dark gunk coating its craters. When Cassini analyzed it, the data pointed to complex organic compounds, possibly mixed with frozen hydrocarbons. Some researchers think it's the same material found on Saturn's other moons, like Phoebe's dark dust, but why does it collect so selectively inside Hyperion's pits? One theory suggests the moon's weak gravity can't hold onto loose surface material, so when sunlight hits the brighter ice, it vaporizes, leaving behind the heavier, darker stuff to accumulate in the shadows. Another wild idea: the craters might act like cold traps, capturing drifting particles from space like cosmic flypaper. The real kicker: Hyperion might be a time capsule. Its porous structure and strange chemistry could preserve clues about the early solar system, back when planets and moons were still clumping together from debris. Unlike geologically active worlds, Hyperion's surface hasn't been resurfaced by lava or erosion. It's a frozen snapshot of chaos, a relic of the violence that shaped our cosmic neighborhood. Every pit, every streak of that eerie dark material tells a story we're still deciphering. So while other moons might steal the spotlight with their oceans or auroras, Hyperion lingers in the background, a crumpled, enigmatic footnote. It doesn't care about symmetry or stability. It's a reminder that even in a universe governed by physics, there's always room for an oddball, a moon so strange it defies every expectation. And that's exactly what makes it unforgettable. If Saturn's other moons feel alien, Titan is downright surreal, a world where rivers carve valleys through dunes of plastic sand, where raindrops fall as liquid methane, and where lakes stretch wider than the Great Lakes of North America. But filled not with water but with hydrocarbons, this isn't science fiction. It's the only place in our solar system besides Earth with a full-fledged liquid cycle, a mirror universe where methane plays the role of water. Picture standing on Titan's shore. The horizon would glow orange under a perpetual haze, the air thick as soup, and the lake before you would ripple with currents of liquefied natural gas. What makes Titan's methane lakes possible is its freakishly dense atmosphere, 1.5 times thicker than Earth's, a blanket of nitrogen and methane that traps heat just enough to keep hydrocarbons in liquid form. While other moons are bare rocks or ice, Titan's atmosphere acts like a pressure cooker, creating conditions so Earth-like that when the Huygens probe landed in 2005, its sensors recorded humidity. But here's the twist: Titan's weather runs on a cryogenic thermostat. At -290 degrees Fahrenheit, water is harder than granite, and methane, a gas on Earth, flows like gasoline. The lakes themselves are uncanny. Near the poles, vast basins like Kraken mere larger than the Caspian Sea ebb and flow with tides, not from our moon but from Saturn's gravitational pull. Radar images show shorelines etched by evaporation, proving these aren't static puddles, they're dynamic, with methane evaporating, forming clouds and raining back down. Some lakes even appear to be karstic, dissolving the icy bedrock beneath like limestone in a terrestrial cave. But the real stunner, Cassini spotted transient, magic islands, mysterious bright patches that appear and vanish in radar scans. Some scientists suspect these could be methane bubbles or floating icebergs of frozen organic sludge, a phenomenon with no earthly parallel. Then there's the subsurface ocean. Beneath Titan's icy crust, a global saltwater sea might slosh, sandwiched between layers of high-pressure ice. This raises a tantalizing question. If life exists there, could it metabolize acetylene instead of glucose, breathing hydrogen instead of oxygen? The chemistry checks out. Titan's atmosphere is a factory for complex organic molecules, raining tholins tar-like compounds that could potentially fuel exotic microbes. The haunting beauty of Titan is how familiar it feels, a distorted reflection of Earth, where familiar processes play out with alien ingredients. It challenges our definitions of habitability, whispering that life might thrive in the unlikeliest corners of the cosmos. Every lake, every methane thunderstorm is a clue waiting to be deciphered. And the biggest mystery of all, what stirs beneath those inky depths where sunlight never reaches and the rules of biology might be rewritten? Every 30 years or so, Saturn unleashes a tempest so vast it could swallow Earth whole, a churning, white-hot cyclone known as the Great White Spot. Unlike the fleeting storms we see on other planets, this monster doesn't just rage in one region. It wraps itself around Saturn's equator like a seething belt, stretching tens of thousands of miles. The sheer scale is staggering: hurricane-force winds, lightning bursts brighter than the sun, and cloud towers that punch hundreds of miles into the sky. Then, just as suddenly as it appeared, the storm vanishes without a trace, leaving astronomers scratching their heads. Why does this celestial tantrum erupt like clockwork? And what shuts it off with such eerie precision? The pattern is uncanny. Since the first recorded observation in 1876, the Great White Spot has appeared roughly every 28 to 30 years, coinciding with Saturn's northern hemisphere summer. That timing is no accident. Saturn's tilt creates seasons just like Earth's, but each one lasts over 7 years, plenty of time for sunlight to slowly cook the atmosphere, building up energy until it explodes. Think of it like a pressure cooker left on too long. As summer heat penetrates deeper into Saturn's upper layers, it destabilizes the dense hydrogen below, triggering colossal updrafts that spiral into a planet-wide fury. But the real mystery isn't the storm's birth, it's its death. Unlike Jupiter's great red spot, which has churned for centuries, Saturn's megastorm dissipates within months as if someone flipped a switch. Some scientists suspect the storm essentially exhausts itself, its energy sapped by the very winds it generates. Others propose a more intriguing idea, that the storm's own rain could be its downfall. As ammonia-laden clouds rise, they cool into crystals that fall like a trillion tiny anchors, dragging heat downward and strangling the convection that fuels the tempest. It's a self-destruct mechanism built into the storm's DNA, nature's way of hitting the reset button. Then there's the wild card, Saturn's internal heat. The planet radiates 2.5 times more energy than it receives from the Sun, a leftover furnace from its formation 4.5 billion years ago. This hidden warmth might act like a throttle, controlling how deep the storm digs into the atmosphere. If it plunges too far, it could tap into warmer, more stable layers that dampen its fury. That could explain why the Great White Spot never evolves into a permanent fixture like Jupiter's. It's starved of the deeper energy needed to sustain itself. The implications go beyond Saturn. Studying these megastorms helps unravel how planetary atmospheres evolve, how heat and wind interact across vast scales, even how gas giants beyond our solar system might behave. Each eruption leaves behind chemical signatures, altering Saturn's atmospheric chemistry for years. It's a reminder that even the mightiest planets aren't static. They breathe, convulse, and reinvent themselves in ways we're only beginning to grasp. When the next great white spot emerges, likely in the 2030s, it won't just be a spectacle. It'll be a front-row seat to one of the solar system's most awe-inspiring mysteries, a chance to witness the invisible forces that shape a giant. Until then, Saturn keeps its secrets, its atmosphere deceptively calm, biding time until the next explosion rewrites the rules all over again. Saturn's atmosphere should be rich with ammonia. At least that's what every textbook and planetary model predicted. This gas, a staple of gas giant chemistry, ought to swirl freely in the upper layers, just like it does on Jupiter. But when scientists analyzed data from the Cassini spacecraft, they hit a baffling snag. Saturn's ammonia levels were suspiciously low, almost as if someone had scrubbed the gas from the upper atmosphere. Where did it all go? The answer might rewrite our understanding of how these colossal planets work. One leading theory is that Saturn's ammonia is literally raining out of the sky. Here's how it could happen. Deep in the atmosphere, where pressures are crushing and temperatures soar, ammonia dissolves into liquid water droplets. Yes, water exists there, trapped in a bizarre, superheated state. These droplets grow heavier until they plunge downward like a celestial hailstorm, pulling ammonia deep below where our instruments can detect it. Imagine a planet-sized distillery with ammonia acting like the alcohol that condenses and falls, leaving the upper layers curiously depleted. This rainout process could explain why Saturn's upper clouds appear ammonia poor compared to Jupiter's. But there's a catch. Even accounting for rainout, some scientists argue the numbers don't fully add up, meaning another process might be at play. Enter the mushball hypothesis. Ammonia doesn't just dissolve in water. It combines with it to form a slushy, hail-like substance that's far denser than gas. These ammonia-rich mushballs could plummet through Saturn's layers at shocking speeds, effectively hiding the gas from view. It's like tossing a handful of snow into a lake. Once it sinks, you'd never know it was there. Then there's the wild card, an unknown layer or chemical reaction deep within Saturn's belly. Some researchers propose that ammonia might be reacting with other compounds under extreme pressure, transforming into entirely new molecules we haven't even identified yet. Hydrogen sulfide, for instance, could bond with ammonia to form ammonium hydrosulfide, a compound that would cloak the missing gas in plain sight. Or perhaps there's a stratification effect where Saturn's internal circulation sequesters ammonia in a hidden reservoir, like a cosmic storage unit we can't access. The implications stretch beyond Saturn. If ammonia is being actively removed or transformed inside gas giants, it challenges assumptions about atmospheric composition across the universe. Exoplanet models, which often rely on ammonia as a key tracer, might need recalibrating. Even more intriguing, this missing ammonia could be a clue to Saturn's internal dynamics, how heat moves, how storms brew, even how the planet formed billions of years ago. Every undetected molecule is a whisper from the depths, hinting at processes we've yet to imagine. So while Saturn's missing ammonia might sound like a niche puzzle, it's really a planetary detective story. The culprit could be rain, chemistry, or something even stranger. Until we send another probe into those golden clouds, the mystery lingers, a reminder that even the most familiar planets still guard their secrets fiercely. Saturn's moon Mimas should be the most boring place in the solar system, a frozen, cratered ice ball with no atmosphere, no obvious geologic activity, and a surface so ancient it's practically a museum of early solar system impacts. That's what scientists thought until they saw its thermal signature, and suddenly, this unremarkable moon became the star of one of the weirdest cosmic mysteries, a heat map that looks uncannily like Pac-Man. When NASA Cassini spacecraft scanned Mimas in infrared, expecting to see a uniform, chilly wasteland, it instead found a bizarre V-shaped hot zone trailing behind the moon like a cosmic wake. The warmer regions formed a near-perfect arc, with temperatures around -310 degrees Fahrenheit toasty compared to the surrounding areas at -340. The resemblance to the classic video game character was so striking, researchers couldn't resist nicknaming it the Pac-Man effect. But this isn't some celestial joke, it's a genuine enigma that defies everything we know about how small, dead moons should behave. So why does a moon just 250 miles wide have a heat map straight out of an arcade? One theory points to Mimas's surface texture. The warm regions might be packed with loose, powdery ice that retains heat slightly better than the surrounding compacted ice, like a thermal blanket draped over part of the moon. But here's the odd part: the pattern doesn't match the distribution of sunlight, ruling out simple solar heating. Instead, it aligns eerily with Mimas's orbit, as if the moon's movement through Saturn's magnetic field is somehow generating the warmth. Then there's the wilder possibility: hidden activity beneath the ice. Mimas is famous for its enormous Herschel crater, which makes it look like the Death Star, but until now, no one suspected anything alive beneath that battered shell. Yet the Pac-Man anomaly hints at something stirring below. Could tidal forces from Saturn be flexing Mimas enough to generate friction, warming its interior like a bent paperclip? It's a long shot. The moon lacks the geysers or cracks seen on Enceladus, but the thermal spike suggests something is breaking the rules. The real puzzle is why this effect appears so sharply defined. If surface texture were the sole culprit, the transition between warm and cold zones should be gradual. Instead, the Pac-Man boundary is razor-sharp, as if drawn by an invisible hand. Some researchers speculate charged particles from Saturn's magnetosphere might be sandblasting one side, altering the ice's properties in a way that traps heat. Others wonder if Mimas's orbital resonance with other moons creates standing waves of energy, concentrating warmth in that peculiar V shape. Whatever the cause, Mimas's Pac-Man is more than a curiosity. It's a reminder that even the quietest corners of our solar system can hide surprises. A moon we wrote off as geologically dead might still have tricks up its sleeve, whispering secrets in the language of heat and ice. Until we land a probe there, this pixelated mystery will keep taunting us, proving that sometimes reality is stranger than any arcade game. Phoebe doesn't belong. While Saturn's other moons orbit in neat, predictable circles, this outlier spins backward, moving against the planet's rotation like a cosmic rebel. Its path is steeply tilted, erratic, almost defiant, as if it weren't born into Saturn's family at all but snatched from the deep freeze of the outer solar system. And that's exactly what scientists suspect. Phoebe might be a fugitive, a stolen relic from the Kuiper belt, hurled inward by gravitational chaos billions of years ago and captured by Saturn's gravity. This isn't just another moon, it's a time capsule from the solar system's violent youth, wearing its history on its sleeve. The evidence is written in its surface. Unlike Saturn's icy, reflective moons, Phoebe is dark, soot-black, absorbing 90% of the sunlight that hits it. Cassini's close flyby in 2004 revealed a battered world, pockmarked with craters and streaked with bright ice exposed by fresh impacts. But the real shocker was the composition. Phoebe is packed with water ice, carbon dioxide, and organic molecules, a cocktail more suited to the frigid edges of the Kuiper belt than Saturn's neighborhood. It's as if this moon rolled through a cosmic paint factory, gathering layers of primordial grime before being tossed into its chaotic orbit. Then there's the orbit itself, wildly elliptical, taking Phoebe millions of miles away from Saturn before swinging it back in close. This isn't just irregular, it's unstable, the kind of path that usually ends with a moon ejected into space or smashed into the planet. Yet Phoebe persists, locked in a gravitational tug of war with Saturn and its rings. Some researchers believe this dance is temporary, that given enough time, Phoebe's orbit will decay, or Saturn's gravity will rip it apart to form a new ring. Until then, it's a living lesson in celestial mechanics, a reminder that not all moons play by the same rules, but the most tantalizing clue: Phoebe might be the source of Saturn's dark pollution. Its surface constantly sheds dust and debris, some of which spirals inward to stain other moons like Iapetus, painting their leading hemispheres charcoal black. In a way, Phoebe's chaos is contagious, leaving fingerprints across the entire Saturn system. What's left is a puzzle wrapped in ice and carbon. If Phoebe truly is a captured Kuiper belt object, it could hold secrets about the early solar system's composition, how materials were distributed, how planets scavenged building blocks from the outer darkness. Every crater, every spectral signature is a word in a story we're still learning to read. And perhaps the most humbling thought, Phoebe's chaotic journey might not be unique. It could be one of countless wanderers flung across the solar system by ancient collisions, a silent witness to the turbulence that shaped our cosmic backyard. Saturn's rings seem pristine from afar, a symphony of ice and dust orbiting in perfect harmony until you look closer and spot the ghostly streaks slicing across them like phantom fingers. These are the mysterious spokes, transient radial features that appear and vanish like clockwork, rotating in lockstep with Saturn's magnetic field rather than obeying the laws of orbital mechanics. Imagine drawing straight lines from the center of a vinyl record to its edge, except this record is 70,000 miles wide, made of ice and floating in space. The spokes defy intuition, hovering above the ring plane as if held aloft by invisible strings, their shadowy forms contrasting sharply with the glittering ice below. What creates these celestial chalk marks? One leading theory points to tiny charged particles lifted electrostatically from the ring material, like dust clinging to a balloon after you rub it on your hair. Micrometeoroids bombarding the rings might kick up clouds of debris, which then become trapped in Saturn's magnetic field, aligning into those eerie linear formations. But here's the twist: these spokes aren't random. They're seasonal, vanishing when Saturn's rings are edged onto the Sun and reappearing as the planet tilts, as if sunlight itself flips a switch. This suggests photons from the Sun might be ionizing the ring particles, charging them just enough to levitate and align. Yet electromagnetism alone might not tell the whole story. Some researchers propose a more dynamic origin. temporary moonlets or clumps of ice hidden within the rings, stirring up wakes that manifest as spokes. Others speculate that Saturn's own auroras could play a role, channeling energy into the rings like a cosmic circuit. The most baffling part, spokes don't appear uniformly. Sometimes they cluster in specific regions, other times they scatter unpredictably, as if Saturn's magnetic field has moods, alternately coaxing them into existence or suppressing them entirely. The debate isn't just academic. Understanding spokes could reveal hidden forces shaping the ring's evolution. Are they a fleeting phenomenon, or do they leave lasting scars? Do they redistribute material, subtly altering the ring's structure over millennia? Every time these ghostly streaks reappear, they taunt us with questions that Cassini's data alone can't answer. Future missions might need to orbit Saturn during its spoke season, armed with instruments sensitive enough to catch these phantoms in the act. One thing's certain, the spokes aren't mere decoration. They're a window into the invisible forces sculpting Saturn's iconic rings, a reminder that even the most serene cosmic vistas hum with unseen energy. Whether powered by meteoroid impacts, electromagnetic tricks, or something even stranger, these fleeting marks prove that Saturn's rings are anything but static. They're alive with mystery, whispering secrets in a language of shadow and light. Rhe shouldn't have oxygen. As Saturn's second largest moon, it's a frozen, airless world where temperatures plunge to -300 degrees Fahrenheit, the kind of place where molecules should hunker down, not float freely as gas. Yet when Cassini skimmed past Rhe in 2010, its instruments picked up a ghostly whisper, a wispy envelope of oxygen and carbon dioxide, so thin it makes Earth's stratosphere feel like soup. This wasn't just unexpected, it was revolutionary. How could a moon with no volcanic activity, no magnetic field, and no liquid water sustain even a trace of breathable air? The answer might rewrite what we know about icy moons and where life could hide. The leading theory starts with Saturn itself. Rhe orbits deep within the planet's magnetosphere, a swirling sea of charged particles trapped by Saturn's magnetic field. As these high-energy protons and electrons slam into Rhe's surface, a mix of water ice and dark organic compounds, they blast apart molecules, liberating oxygen atoms in a process called radiolysis. Picture a cosmic bullet hitting an icy target. The impact fractures water ice into hydrogen, which escapes into space, and oxygen, which lingers just long enough to form this phantom atmosphere. Over billions of years, this relentless particle rain could have turned Rhe's entire surface into an oxygen factory, with each square inch of ice contributing atoms to the moon's invisible shroud. But here's the puzzle. If radiolysis were the sole source, Rhe's oxygen should be accompanied by hydrogen gas, yet Cassini found none. This suggests something else is at play. One possibility, the oxygen might be seeping from ancient reservoirs trapped beneath the ice, remnants of primordial chemistry locked away during Rhe's formation. Another wild idea involves carbon dioxide, which Cassini detected alongside oxygen. This gas shouldn't survive long under Saturn's radiation unless it's constantly replenished, perhaps by subsurface dry ice sublimating through cracks or even organic molecules breaking down under the bombardment. The implications are staggering. If Rhe's oxygen comes from surface ice alone, it hints that any icy moon bathed in radiation, from Jupiter's Europa to distant Pluto, could harbor similar tenuous atmospheres. But if the gas originates deeper, it raises the tantalizing prospect of hidden chemistry beneath Rhe's crust, maybe even pockets of liquid water where oxygen dissolves like bubbles in a soda. Either way, this moon is proof that airless worlds might not be so lifeless after all. What's most humbling is how fragile this atmosphere is. Rhe's oxygen is so sparse, you'd need to compress a volume the size of a football stadium to fill a single breath. It's constantly leaking into space, only sustained by an endless cycle of destruction and renewal. Yet that delicate balance makes it a laboratory for processes we can't replicate on Earth, a place where the universe tests the limits of chemistry in extreme environments. Rhee's mystery isn't just about oxygen, it's about redefining where we look for the building blocks of life. If a frozen moon can conjure an atmosphere from ice and starlight, what else might be possible in the quiet corners of our solar system? The answer is written in those vanishing traces of gas, a cosmic exhale we're only beginning to measure. Dione hides its scars with elegance, a moon once thought dead, now bearing bright, jagged fractures that slice across its icy plains like luminous lightning bolts. These are the so-called wisps, ethereal tendrils stretching hundreds of miles, their gleaming contrast against the dark, cratered terrain so striking that Voyager scientists initially mistook them for cryovolcanoes, spewing fresh ice instead of lava. But when Cassini returned decades later with sharper eyes, the truth proved even stranger. These weren't eruptions at all. They were cliffs, sheer walls of ice towering over valleys, their faces reflecting sunlight like celestial mirrors. The mystery: why does a moon barely 700 miles wide have fractures so massive, so organized that they look less like random cracks and more like the deliberate strokes of a cosmic artist? The leading theory points to Dione's tortured past. Like a ball of ice gripped in Saturn's gravitational fist, this moon has been flexed and strained over eons, its crust stretched until it split. The wisps might be tectonic scars, evidence of a subsurface ocean that once surged and froze, expanding to fracture the surface like an overfilled water bottle left in the freezer. Some fractures run parallel for miles, suggesting they formed during a single catastrophic event, perhaps a tidal tug of war with neighboring moons or a dramatic shift in Dione's rotation. Others intersect at sharp angles, hinting at multiple episodes of stress, each leaving its mark like layers in a geological diary. But here's where the debate ignites. If Dione's cracks came from ancient forces, why do some appear startlingly fresh, with few craters marring their bright surfaces? One faction argues these fractures are actively rejuvenating, their faces kept clean by occasional landslides or even trace amounts of gas venting from below. Others propose a more unsettling idea, that Dione's ice shell might still be moving, creeping slowly over a hidden ocean like Earth's tectonic plates, except here, the rock is ice and the magma is slush. Cassini's gravity measurements lend weight to this, showing Dione's interior is denser than expected, possibly housing a subsurface sea even today. Then there's the enigma of the tiger stripes, not to be confused with Enceladus's famous fissures, but eerily similar in their linear perfection. These features, concentrated near Dione's equator, seem too orderly for random cracking. Could they be the surface expression of a deep fault system, a network of weaknesses where the moon's crust tore apart under stress? Or do they point to something more exotic, like tidal heating concentrating along specific lines, softening the ice until it fractured in precise, repeating patterns? The wisps aren't just geological curiosities, they're time capsules. Every cliff, every valley holds clues to Dione's thermal history, its relationship with Saturn, even the potential for habitability. If fresh ice really is exposed sporadically, it could mean organic molecules or salts are being brought to the surface, creating niches where weird chemistry might unfold. And if that subsurface ocean still exists, however thin, it would place Dione in an elite club of moons where life could cling to the shadows. What makes these fractures so haunting is their silence. They don't spew plumes like Enceladus or glow with auroras like Europa. They just sit there gleaming mutely, as if guarding secrets too old to share. Yet in their stillness, they whisper of a world far more dynamic than we ever imagined, a moon that refuses to be just another frozen relic, demanding we reconsider what dead really means in the outer solar system. So while Dione's wisps might lack the drama of erupting geysers or methane lakes, they hold their own kind of magic. a reminder that even the quietest worlds can harbor tectonic heartbeats, their stories etched in ice and light, waiting for us to read between the lines. Saturn's south pole should be one of the coldest places in the solar system, a frozen wasteland where sunlight barely grazes the atmosphere. But when scientists pointed their instruments at this shadowy realm, they got a shock. A blistering hot vortex with temperatures soaring to nearly 200 degrees Fahrenheit hotter than anywhere else on the planet. This isn't just a mild anomaly, it's a full-blown thermal explosion, defying every model of planetary weather. How does a pole shrouded in darkness for years at a time become a furnace hotter than some regions bathed in constant sunlight? The answer might lie in forces so powerful they rewrite the rules of atmospheric physics. At the heart of this mystery is Saturn's aurora, a shimmering ring of light dancing around the South Pole. On Earth, auroras paint the sky with pretty colors, but on Saturn, they're engines of chaos. Charged particles from the solar wind slam into the planet's magnetic field, funneling energy downward like a cosmic lightning rod. This bombardment doesn't just create light shows, it superheats the upper atmosphere, driving winds that spiral into a vortex tighter and faster than any hurricane. The result, a high-altitude oven trapped inside a polar cage where temperatures spike to levels no one saw coming. Yet auroral heating alone can't explain the extreme numbers. Saturn's south pole isn't just warm, it's scalding, with layers of the atmosphere reaching temperatures comparable to some parts of Mercury. One theory suggests hidden waves rippling through the atmosphere like sound in a pipe could be compressing and heating the gas as they travel. Another wild idea points to Saturn's own internal heat, leaking upward and colliding with the auroral energy in a feedback loop that turbocharges the vortex. Imagine a pot of water boiling on a stove, but the stove is also being zapped by a blowtorch. That's the kind of chaotic energy cocktail we're dealing with here. The real enigma is the vortex's shape. Unlike the orderly hexagon at the North Pole, this southern maelstrom is a churning, circular beast, its winds whipping at over 300 miles per hour. It's as if someone dropped a giant mixer into Saturn's atmosphere and let it spin out of control. And while most storms eventually dissipate, this one persists, locked in place by forces we're only beginning to map. What makes this discovery so thrilling is what it reveals about energy flow in gas giants. Saturn isn't just passively absorbing sunlight, it's a dynamic, seething cauldron of hidden forces where magnetic fields, internal heat, and solar radiation collide in ways we never anticipated. Every scorching degree at that South Pole is a clue, a fingerprint of processes that might govern atmospheres light years away. Until we send another probe into those golden clouds, this ultra-hot vortex will keep burning, a fiery question mark at the edge of our understanding. Saturn's F-ring is the solar system's most mischievous ribbon of ice, a narrow, twisted band that refuses to behave like the planet's other orderly rings. Instead of circling Saturn in smooth, predictable arcs, this ring kinks, braids, and even sprouts strange glowing clumps that appear and vanish like cosmic sleight of hand. The culprits are elusive moonlets, some no bigger than skyscrapers, whose gravitational tugs warp the ring into ever-shifting sculptures. But here's the mystery. Are these moonlets solid objects or just temporary clumps of debris that form and dissolve like sandcastles in a tidal breeze? When Voyager first spotted the F-ring's bizarre structures in the early 1980s, scientists were baffled. Some sections looked like they'd been threaded through a braiding machine, while others had bright knots that flickered in and out of existence. The Cassini mission later revealed the likely architect's tiny moonlets, some embedded within the ring itself, others orbiting just outside, their gravity carving out waves, loops, and channels in the ice. One, nicknamed Pandora's Accomplice, even seems to shepherd the ring's outer edge, keeping its material from drifting away into space. But the real intrigue lies in the moonlets we can't see directly. These phantom objects reveal themselves only through their footprints, sudden kinks or brightened patches where their gravity has gathered ice particles into temporary crowds. The debate isn't just academic. If these moonlets are solid bodies, they could be remnants of a shattered moon, survivors of some ancient collision that left them to wander the ring's edge. Their stability would mean the F-ring is far older than its chaotic appearance suggests, with these tiny shepherds maintaining its structure over eons. But if they're transient clumps, aggregates of ice that form and disperse under Saturn's tidal forces, then the F-ring becomes a live-action demo of how planets and moons might have coalesced from dust in the early solar system. Picture a celestial construction zone where rubble piles up into temporary moons only to be torn apart again, a cycle of creation and destruction playing out in real time. Cassini's closest encounters added fuel to the fire. Some clumps vanished within hours, suggesting fragile, snowball-like assemblages, yet others left gravitational signatures hinting at denser cores, maybe even rock-hard nuclei hidden beneath their icy shells. The wildest twist, a few moonlets seemed to migrate, drifting through the ring like ghosts, their paths defying straightforward orbital math. One explanation: they're caught in a tug-of-war between Saturn's gravity and the tidal pull of larger moons like Prometheus, which periodically dips into the F-ring, stirring up chaos like a spoon through syrup. What makes the F-ring moonlets so mesmerizing isn't just their mystery, it's the fleeting artistry they create. A braid might unravel in weeks, a glowing knot could flare and fade before another spacecraft ever sees it. This isn't just orbital mechanics, it's performance art on a planetary scale, with gravity as the choreographer, and the show never stops. Every kink, every clump, is a snapshot of forces we're still learning to measure, proving that even the tiniest objects can leave the boldest scars on the cosmos. So while Saturn's other rings might be studied like history books, the F-ring is a living diary, its pages scribbled in ice and erased by time. Whether its moonlets are permanent actors or transient extras, they're rewriting our understanding of how delicate and dynamic the universe's smallest architects can be. Among Saturn's many icy moons, Tethys hides a crimson secret, thin, jagged streaks slashing across its surface like claw marks dipped in rust. These so-called red arcs stretch for hundreds of miles, yet they're so narrowly concentrated that from space they look like someone took a paintbrush to the moon's frozen canvas. The strangest part, these aren't random stains. They follow precise geologic patterns, tracing fractures in Tethys's icy crust as if the moon itself is bleeding from invisible wounds. So what paints a moon red? One leading theory points to chemical impurities, compounds like tholins, complex organic molecules that form when radiation zaps simple ices. These reddish-brown gunk piles up where Tethys's surface is most stressed, oozing from cracks like cosmic sap. Picture freezing a bottle of soda until it bursts. The sticky residue left behind might resemble these eerie streaks. But there's a catch. If radiation alone were responsible, the coloring should be more widespread, not laser-focused along these razor-thin lines. That's where the moon's violent history comes in. Tethys bears a colossal scar, Ithaca Chasma, a canyon system so vast it spans 3/4 of the moon's circumference. The red arcs seem to hug this tectonic network, suggesting they're fed by underground reservoirs of volatile chemicals, possibly venting through cracks too small for our cameras to spot. Every time Tethys flexes under Saturn's gravitational pull, these fractures might exhale traces of trapped gas, which then freezes and darkens under relentless radiation. Yet the concentration remains baffling. Why don't these chemicals diffuse across the surface? One clue lies in Tethys's pristine ice. Most of the moon reflects sunlight like a mirror, meaning its surface is too cold and inert for contaminants to spread far. The red material might only stick where fresh ice is exposed. Think of it like dye injected into a glacier, staying trapped in the veins where the ice splits. Another twist, electromagnetic forces. Saturn's magnetic field funnels charged particles toward Tethys' equator, where many red arcs cluster. This particle rain could be etching the ice, selectively darkening certain regions like a cosmic etching tool. But why some fractures glow crimson while others stay untouched is anyone's guess. The arcs might be more than geologic quirks, they could be windows. If the reddish tint comes from organics, it hints at a subsurface chemistry richer than we imagined. If it's radiation's handiwork, it reveals how Saturn's magnetic field sculpts its moons down to the molecular level. Every streak is a puzzle, a whisper from a moon that refuses to be just another frozen orb. And until we land a probe there, those crimson slashes will keep taunting us, a reminder that even the quietest worlds wear their scars in color. For decades, scientists believed they'd cracked Saturn's rotation rate by listening to its heartbeat, a steady pulse of radio waves, ticking like a cosmic metronome every 10 hours and 39 minutes. These emissions, dubbed Saturn kilometric radiation, seemed like the perfect clock, synced to the planet's magnetic field and, by extension, its deep interior. But then the unthinkable happened. The clock started drifting. By the time Cassini arrived, the pulses had slowed by a baffling 6 minutes, as if Saturn itself had hit the snooze button. This wasn't just a hiccup, it was a fundamental challenge to how we measure time on gas giants. The mystery hinges on Saturn's invisible engine, its magnetic field. Unlike Earth, where the magnetic poles align roughly with the geographic ones, Saturn's field is eerily symmetrical, almost perfectly aligned with its axis of rotation. That symmetry should make its radio pulses ultra-precise, tied to the planet's core like a tachometer reading, yet something's throwing off the signal. One leading theory blames the rings. As they orbit, they might be dragging charged particles along Saturn's magnetic field lines, creating a braking effect that subtly slows the apparent rotation rate. Picture a spinning top wrapped in a scarf. The fabric's friction would gradually alter the top's spin, even if the core kept its original speed. Then there's the atmosphere. Saturn's churning layers of hydrogen act like a giant dynamo, generating currents that shape the magnetic field. But unlike Jupiter's turbulent skies, Saturn's winds are oddly synchronized at high altitudes, possibly creating a drag on the magnetic field that decouples it from the planet's interior rotation. Imagine stirring a cup of coffee with a spoon. The liquid moves at different speeds depending on depth, and the spoon here, the magnetic field might not rotate at the same rate as your hand, the core. The wild card, Saturn's seasons. The planet's tilt means its magnetosphere interacts with the solar wind differently over its 30-year orbit, potentially tweaking the radio pulse timing like a cosmic interference signal. Cassini observed this firsthand. As Saturn approached equinox, the pulse period began to shift, hinting that sunlight itself might be puppeteering the magnetic field in ways we don't yet grasp. What's at stake isn't just a number, it's our understanding of gas giants' hidden mechanics. If we can't pin down Saturn's rotation, models of its interior structure, weather patterns, even its formation history start to wobble. The radio clock was supposed to be a bedrock measurement, yet it's proven as slippery as the planet's gaseous layers. Future missions might need to peer beneath the clouds, using gravity maps or seismic vibrations to hear Saturn's true pulse. Until then, those shifting radio waves remain a cosmic taunt, a reminder that even the most precise tools can't always measure the universe's chaos. Most moons follow predictable paths, content to circle their planets in solitude, but not Helene. This tiny, irregularly shaped moon plays cosmic hide-and-seek, sharing its orbit with the much larger Dione in a delicate gravitational dance. Known as a Trojan moon, Helene doesn't trail behind or lead ahead of its orbital partner. It's locked precisely 60 degrees in front, occupying one of two stable points called Lagrange points, where the gravitational pulls of Saturn and Dione perfectly balance. It's as if the universe carved out a special parking spot, a gravitational eddy where Helene can loiter indefinitely without drifting away or crashing into its neighbor. The mechanics of this arrangement are nothing short of celestial wizardry. Picture a vast, invisible triangle in space with Saturn at one corner, Dione at another, and Helene holding steady at the third. This Lagrange point, specifically L4, acts like a gravitational sweet spot where the combined forces create a pocket of stability. Normally, such delicate balances are theoretical, existing only in textbooks, but here's the proof. Helene has likely occupied this spot for billions of years, a testament to orbital physics in action. The Moon isn't alone in this peculiar club. Its smaller sibling, Polydeuces, orbits 60 degrees behind Dione at the L5 point, completing the trio. Together, they form one of the solar system's few confirmed Trojan systems, a rare example of cosmic harmony. But how does something like this form in the first place? The leading theory suggests Helene and Polydeuces are remnants of a larger collision, fragments of a moon or passing object that shattered eons ago and were captured in these orbital safe zones. Alternatively, they might have formed in place, coalescing from the same debris disk that birthed Dione, their paths fine-tuned by Saturn's immense gravity over time. What's certain is that their stability defies intuition. Even slight gravitational nudges from other moons should have ejected them long ago, yet they persist silent witnesses to the precision of celestial mechanics. What makes Helene even more intriguing is its surface. Unlike the heavily cratered Dione, Helene appears smoother, with strange, flowing grooves and dimples that hint at a turbulent past. Some scientists speculate it might be coated in fine dust, kicked up by micrometeorite impacts or even geysers long since dormant. Others propose its odd shape, like a lumpy potato, could mean it's a loosely packed rubble pile, held together by weak gravity and the occasional gravitational squeeze from Dione. Every close-up image from Cassini adds another layer to the mystery, revealing a world that's both a prisoner and a beneficiary of its peculiar orbit. Trojan moons like Helene aren't just curiosities, they're cosmic time capsules. By studying their orbits, we unlock clues about Saturn's early history, the violence that shaped its moon system, and even the conditions that allow such delicate equilibriums to exist. They're proof that even in the chaos of space, there are pockets of perfection where gravity and motion conspire to create something extraordinary. And as we search for Trojans around other planets, or even exoplanets, Helene stands as a reminder that the universe loves balance as much as it loves surprises. Titan's methane should be gone by now. On a moon where hydrocarbons rain from the sky, flow in rivers, and pool into vast lakes, basic chemistry says the methane ought to have broken down under sunlight billions of years ago, leaving Titan as dry as a bone. Yet here we are. Cassini's radar images show liquid methane sloshing across the surface today, as fresh as if it were just replenished. This cosmic contradiction has scientists scrambling. Where is all this methane coming from? The answer might lie beneath Titan's icy crust, in hidden reservoirs or processes we've only begun to imagine. First, consider the math. Sunlight hitting Titan's upper atmosphere splits methane molecules apart, with the fragments recombining into heavier hydrocarbons like ethane and acetylene. Over geologic time, this should have drained Titan's methane supply entirely. Even accounting for occasional cometary deliveries, the numbers don't add up unless something is actively refilling the tank. One compelling theory points to cryovolcanoes, icy vents spewing methane from deep within the moon. Cassini spotted what might be these volcanic features, dome-like structures with flow patterns resembling lava, except here, the lava could be a slush of water, ammonia, and methane erupting from a subsurface ocean. If Titan's interior is geologically active, it might be pumping methane to the surface like a frozen Yellowstone, replenishing what sunlight destroys. Then there's the reservoir hypothesis. Beneath Titan's frozen shell, vast pockets of liquid methane could be trapped in porous ice or dissolved in a subsurface ocean, slowly leaking through cracks like a planetary oil field. Some models suggest these reserves might connect to the surface lakes via a network of underground aquifers, creating a hidden hydrologic cycle. Imagine methane percolating upward, evaporating into the atmosphere, then raining back down. A closed-loop system that sustained itself for eons. But the wildest idea, Titan might be making methane fresh. At extreme pressures and temperatures, chemical reactions between water and minerals like olivine could produce methane abiotically, no biology required. Similar processes occur at Earth's hydrothermal vents, where serpentinization reactions churn out hydrogen and methane. If Titan's ocean floor hosts similar geology, it could be a factory for hydrocarbons, constantly manufacturing new methane to offset atmospheric losses. The implications are staggering. If Titan's methane is actively replenished, it transforms from a static oddity into a dynamic world with a complex carbon cycle, one that might even hint at habitable conditions beneath the ice. Every lake, every storm becomes part of a grander system, one we've barely begun to decode. Until we land a probe on those methane shores, Titan will keep its secrets close, a world where the simplest molecule defies expectation, proving that even the most familiar chemistry can surprise us in alien skies. Saturn isn't just a planet, it's a cosmic billiard table, where invisible high-speed gas clouds zip through its magnetic environment at breakneck velocities. These hypervelocity clouds, detected by the Cassini spacecraft, aren't your average space weather. They're chaotic streaks of ionized gas, some clocking in at speeds over 100 kilometers per second, fast enough to cross the continental United States in under a minute. What's propelling them, and more perplexing, why are these fleeting gas bursts so tightly concentrated near Saturn's rings? The prime suspect, micrometeoroids, tiny debris no larger than grains of sand, pelting Saturn's rings at relentless speeds. When these particles slam into the ring material, the impact vaporizes both the intruder and a minuscule portion of the icy ring, creating a puff of superheated plasma. But here's the twist: instead of dissipating harmlessly, this plasma gets caught in Saturn's magnetic field, accelerating to ludicrous speeds like a cosmic slingshot. Imagine throwing a pebble into a high-voltage power line. The resulting spark isn't just a flash. It's a surge of energy hurled outward by invisible forces. Yet speed alone isn't the only mystery. The composition of these clouds reads like a bizarre chemistry experiment. Cassini's instruments detected traces of water vapor, sodium, and even organic molecules, all signatures of the ring material itself. This suggests the clouds aren't just random space dust, they're literal pieces of Saturn's rings, atomized and launched into the void. Some researchers propose that the rings act like a giant particle accelerator, where impacts trigger chain reactions of ionization, turning ice into plasma with terrifying efficiency. Then there's the question of trajectory. Unlike the steady drift of solar wind, these clouds move in jagged, unpredictable paths, as if Saturn's magnetic field is flicking them away like marbles. One theory points to magnetic reconnection, a process where twisted field lines suddenly snap, releasing bursts of energy that catapult the plasma outward. It's the same phenomenon behind solar flares, but here, it's happening on a smaller, sharper scale, a constant crackle of mini-explosions hidden in Saturn's shadow. The implications are staggering. If hypervelocity clouds are this common near Saturn, they might exist around other ringed planets, or even exoplanets acting as invisible markers of ring systems we can't yet see. They could also be eroding the rings themselves, slowly sandblasting them into oblivion, one microscopic impact at a time. Every plasma streak is a snapshot of destruction and creation, a reminder that even the emptiest spaces between Saturn's rings are alive with violence. What makes these clouds so mesmerizing isn't just their speed or origin, it's their impermanence. They flare and fade in minutes, leaving no trace behind. To witness one is to catch a glimpse of a hidden layer of cosmic chaos, where the universe's smallest collisions ripple outward in ways we're only beginning to measure. And as Saturn's rings continue their slow dance, these hypervelocity ghosts remind us that even the most serene-looking systems are anything but quiet. Most moons stick to their orbits like clockwork, tracing the same path around their planet for eons. But Janus and Epimetheus didn't get the memo. These two tiny moons, each barely 60 miles across, engage in a celestial game of musical chairs, swapping orbits every 4 years in a maneuver so precise it defies intuition. Picture two race cars circling a track, gradually closing the gap until, without colliding or even touching, they seamlessly exchange places. This isn't science fiction. It's an orbital ballet choreographed by gravity itself, a phenomenon so rare we've never seen it anywhere else in the solar system. The mechanics of this swap are nothing short of cosmic wizardry. Janus and Epimetheus orbit Saturn less than 30 miles apart, a hair's width in astronomical terms, yet their paths are separated just enough to avoid disaster. As the inner moon, typically Janus gains speed due to Saturn's gravity. It creeps up on its slower counterpart, but instead of crashing, something extraordinary happens. Their gravitational tug of war flings the faster moon outward while pulling the slower one inward. In that critical moment, they trade velocities and trajectories, each assuming the other's orbital identity like celestial doppelgangers. The entire swap takes mere days, leaving both moons unscathed but forever altered in their cosmic roles. What makes this dance even more remarkable is its predictability. Like clockwork, the moons repeat this maneuver every 4 years, locked in a cycle that's persisted for millennia. Scientists suspect this rhythmic exchange stabilizes their orbits, preventing chaos that might otherwise send one moon spiraling away or crashing into Saturn's rings. It's a self-correcting system, nature's way of maintaining equilibrium through motion. The energy they exchange isn't lost, it's recycled, a perpetual cosmic engine fueled by gravity's push and pull. Yet the origins of this partnership remain murky. Some theories suggest Janus and Epimetheus were once a single moon that fractured under Saturn's tidal forces, leaving behind twin fragments destined to chase each other forever. Others propose their stray debris captured by Saturn's gravity, their orbits fine-tuned over eons into this bizarre synchrony. Either way, their existence challenges our assumptions about orbital dynamics, proving that even the most crowded planetary systems can harbor surprises. The Janus-Epimetheus swap isn't just a curiosity, it's a masterclass in celestial mechanics. Every 4 years, without fail, these moons remind us that the universe loves a well-timed pivot, a delicate negotiation between speed and space that keeps the cosmic dance alive. And as they continue their silent, relentless trade, they whisper a truth astronomers are only beginning to grasp. Sometimes the most stable systems are the ones that never stop moving. From Earth, Saturn's rings gleam like a flawless halo but venture to their unlit side, and that pristine image shatters. In the shadows, eerie dark patches emerge, regions where sunlight refuses to scatter as expected, leaving voids that defy simple explanations. These aren't just empty gaps, they're cosmic puzzles, hinting at hidden structures or bizarre physics playing out amidst the ice. The mystery lies in the way light dances, or doesn't, across the rings. When sunlight strikes the icy particles, it should bounce uniformly, creating the bright, reflective bands we're familiar with. Yet certain zones absorb light like cosmic velvet, appearing almost charcoal black in Cassini's images. One theory suggests these patches harbor ultra-fine dust, particles so small they swallow photons rather than reflecting them. Picture blowing smoke onto a mirror. The glass's shine dulls under the haze. Similarly, micron-sized debris could be smothering sections of the rings, turning them into light traps. But dust alone might not explain the sharp boundaries of these dark regions. Some researchers propose embedded moonlets, chunks of dense material lurking within the ring plane, casting long shadows or stirring up fine debris as they orbit. Others point to electromagnetic effects. Saturn's magnetic field might be sorting particles by size, funneling darker, smaller grains into specific zones like a cosmic conveyor belt. The most tantalizing idea, temporary clumps of ring material collapsing under their own gravity into dense, light-absorbing knots before dispersing again, a cycle of creation and destruction we've barely begun to witness. The strangest clue comes from the ring's thermal signature. Dark regions often radiate more heat than their brighter neighbors, as if they're somehow trapping energy. This could mean their particles are fluffier, with porous surfaces that soak up sunlight like sponges. Alternatively, the darkness might stem from chemical contaminants, complex organics or carbon compounds staining the ice like ink blots. Cassini's data revealed traces of such materials, possibly delivered by meteoroid impacts or migrating from Saturn's darker moons. What makes these shadows so unsettling is their impermanence. Unlike the planet's famous gaps, these patches shift over time, fading or intensifying with Saturn's seasons. Some even seem to pulse, growing darker during equinoxes when sunlight grazes the ring's edge on, as if the angle of light unveils secrets hidden in plain sight. It's a reminder that the rings aren't static art, they're dynamic, evolving structures, where even the absence of light tells a story. The truth may lie in a combination of factors: dust, moonlets, electromagnetic sorting, and chemistry, all conspiring to paint these cosmic bruises. Until we send missions capable of sampling the rings directly, their dark side remains a canvas of speculation, a testament to how much we still don't know about a structure so iconic, we often forget it's hiding anything at all. Of all Saturn's moons, Atlas and Pan seem ripped straight from a 1950s sci-fi flick. Tiny, walnut-shaped worlds with bulging equatorial ridges so pronounced they look like flying saucers parked in orbit. These bizarre formations aren't just superficial quirks, they're structural marvels, with Atlas sporting a ridge nearly 20% of its diameter, as if someone fastened a giant hula hoop around its middle. How does a moon barely 20 miles across grow such a precise, oversized belt? The answer might lie in Saturn's rings themselves, a cosmic construction project playing out over millions of years. One leading theory suggests these ridges are accretion disks gone rogue. As Atlas and Pan plow through Saturn's rings, their gravity tugs on nearby ice particles, funneling them toward the equator like snow piling up on a windshield. Over time, this material could have accumulated into those striking ridges, sculpted by the delicate balance between the moon's weak gravity and Saturn's relentless tides. Picture a snowball rolling downhill, gathering layers until it's more belt than ball. But there's a catch: the ridges appear too smooth, too symmetrical for a purely random process. Some researchers propose that electrostatic forces, tiny charges building up on ice grains, might have guided the material into place, arranging it with unnatural precision. Not everyone's convinced, though. Alternative theories point to ancient collisions where younger, faster-spinning versions of these moons flung loose material outward, only for it to freeze into these equatorial bulges as rotation slowed. Others speculate that the ridges might be remnants of a shattered larger moon, its debris captured and molded by tidal forces into these peculiar shapes. The wildest idea: these moons could be porous rubble piles, their interiors so loosely packed that Saturn's gravity stretched them like taffy, leaving behind permanent equatorial scars. What makes Atlas and Pan truly mesmerizing is their role as cosmic timekeepers. Their ridges might preserve a record of ring dynamics, long vanished clues to how Saturn's rings evolved, how moons interact with their environments, even how delicate structures endure in violent gravitational fields. Every groove, every curve in those ridges holds a story, whether it's written in ice, shaped by tides, or etched by forces we haven't yet named. For now, these flying saucer moons hover in our imagination, defying easy classification. They're not just geological oddities, they're experiments in celestial mechanics, showing us how even the smallest worlds can wear the universe's creativity on their sleeves. And until we land a probe on those razor-thin ridges, they'll keep their secrets spinning silently through the void as proof that sometimes reality outdoes fiction. Lightning on Earth tears open the sky with brilliant flashes, but on Saturn, it's something else entirely. A force of raw, unfiltered power, discharging bolts 10,000 times stronger than anything our planet produces. Yet despite this staggering voltage, Saturnian lightning is oddly secretive, refusing to strike at random like Earth storms. Instead, it clusters in tight, tempestuous zones, erupting only during rare megastorms or within enigmatic vortices like the Dragon Storm. This isn't just a difference in scale, it's a fundamental divergence in how electricity behaves in an atmosphere made of hydrogen and helium, where the very rules of thunderstorms get rewritten. Take the Great White Spot, Saturn's once-in-a-generation megastorm. When this behemoth rages, it doesn't just produce lightning, it becomes a factory for it, generating flashes so intense they can be detected from millions of miles away. But here's the puzzle: these bolts don't scatter across the storm's expanse. They concentrate in narrow bands as if funneled by some invisible force. Scientists suspect this has to do with Saturn's lack of a solid surface. On Earth, lightning needs rising moist air and falling ice crystals to generate charge separation. But Saturn's storms tap into something deeper, possibly layers of water and ammonia sloshing far below the visible clouds, where pressures crush these compounds into exotic, electrically conductive slurries. When these layers shear against each other, the friction might ignite discharges on a scale we can barely comprehend. Then there's the ring's role in this high-voltage drama. Saturn's lightning doesn't just light up the atmosphere, it interacts with the ring system in ways that still baffle researchers. Radio emissions from these mega-bolts spiral along magnetic field lines, sometimes skimming the innermost rings and kicking up waves of charged particles. Cassini even detected eerie, whistler waves, electromagnetic pulses triggered by lightning echoing through the rings like cosmic Morse code. This suggests the rings aren't just passive bystanders, they're part of an electric circuit, with energy leaping between the planet and its icy halo in a feedback loop we're only starting to map. But the real mystery is the scarcity. Why does a planet with such colossal storms produce lightning so sparingly? One clue lies in Saturn's peculiar chemistry. Without Earth's mix of oxygen and nitrogen, its atmosphere may lack the ingredients for frequent charge separation. Another theory points to the planet's internal heat, which could stabilize the upper atmosphere, suppressing the convective turbulence that spawns thunderstorms elsewhere. Or perhaps Saturn's lightning is just stealthier, hidden beneath opaque cloud decks, only betraying itself when a storm punches through to the visible layers. What's clear is that Saturn's lightning isn't just a scaled-up version of Earth's. It's an alien phenomenon shaped by pressures, chemistries, and forces unlike anything in our experience. Every bolt is a probe into the planet's hidden layers, a fleeting signal from depths we've never seen. And until we send a mission capable of enduring those hellish conditions, these electric giants will keep their secrets, flashing in the darkness like encrypted messages from a world that defies every expectation. Saturn has dazzled and baffled us for centuries, a ringed enigma spinning in the void, offering glimpses of its secrets only to yank them away when we get too close. We've marveled at its hexagonal storms, flinched at the dragon's roar of hypercharged lightning, and floated over methane lakes that defy the laws of chemistry. Yet for every mystery solved, like the source of Enceladus's geysers or the origin of Titan's dunes, a dozen more erupt in its place. Why does Saturn's rotation rate keep changing? What unseen force sculpts the perfect edges of its rings? And just how deep does the rabbit hole go beneath those golden clouds, where pressures crush matter into forms we can't even simulate? The humbling truth is that Saturn operates on a logic all its own. We're still decoding the basic rules of its atmosphere, where storms rage for months then vanish without a trace, where jet streams move faster than bullets yet maintain razor-sharp boundaries. Even its iconic rings, those seemingly timeless ribbons of ice, are proving to be shockingly dynamic, with moonlets playing demolition derby and dark matter clumping in ways that shouldn't be possible. Every probe we send, from Voyager to Cassini, peels back a layer only to reveal deeper strangeness underneath. But here's the exhilarating part: the story isn't over. Missions like NASA Dragonfly, set to soar through Titan's hazy skies in the 2030s, or proposed orbiters designed to dive into Saturn's atmosphere, promise to turn these mysteries into revelations. Imagine watching a drone navigate an alien moon's weather system, or tasting the composition of a hypervelocity gas cloud in real time. The next decade could rewrite entire chapters of planetary science, and you'll get to witness it firsthand. So as Saturn continues its slow march across the night sky, remember, it's not just a planet. It's a living classroom, a cosmic lab where the universe experiments with physics we've barely begun to grasp. Which of its secrets fascinates you the most? The hexagonal storm, the missing ammonia, the whispers of life beneath Enceladus's ice? Drop your favorite mystery in the comments, because the conversation doesn't end here. The greatest discoveries often start with a simple question, and Saturn, it's got plenty left to ask.